Good evening to all. This is our 21st lecture session of the course Fluid Mechanics. In the previous lecture, we have completed our discussion on the equation of motion for a fluid particle, where we discussed about the application of Reynolds transport theorem to a property of the fluid which is called as the linear momentum. Okay. It is to bring to your notice that whatever the equation we have studied till now for the linear momentum, that particular equation is applicable in nothing but for the inertial frames of reference. Okay, so can you tell me what do you mean by inertial frame of reference? Yes, frame at rest. Frame at rest or any other frame which is moving at constant velocity, that particular frame is also called as nothing but a inertial frame of reference. Okay, so to demonstrate this, what I will do, I will consider a system over here. Say I have nothing but XYZ coordinate system, and say this is the O as origin, and I am calling this frame as nothing but my O frame. Okay, so say I am calling this particular frame as, let me choose the pen. Okay, so I am calling this as nothing but the O frame. Okay, now I have say another frame which is having XYZ system over here, and this particular frame is nothing but O dash frame. Okay, so I am considering that this O dash frame is nothing but a moving frame. Now if I consider that I have some fluid particle over here, so let me write that this particular fluid particle is having position vector r vector with reference to frame O. Okay, and let us consider that it is having some position vector r dash vector with some reference frame O dash. Okay, and let's also consider that with reference to frame O dash is having position vector capital R vector. Okay, so from here you can see now this is nothing but a in this particular triangular system I can apply the vectors law of addition. So you can see this R vector and R dash vector are being added here we are doing the vector addition of these two. So it means I can write that R dash vector plus R vector, and these are forming nothing but my position vector R vector. So you have to understand that this is my fluid particle under consideration, and for this fluid particle what I am saying is that my R vector is position vector corresponding to frame O, and R dash vector is position vector corresponding to frame O dash, and capital R vector is nothing but my frame of position vector of the moving frame of reference. Okay, so now in this particular equation, if I take the time derivative, then I can write that, let me write the time derivative. So I can write d by dt of r vector equal to d by dt of r dash vector plus d by dt of capital R vector. Okay, so you can see over here that from this particular equation I will be finding the d by dt of r vector will be nothing but velocity of the particle, fluid particle, with reference to frame O, whereas this will be becoming nothing but velocity of fluid particle with reference to frame O dash, and plus dr vector by dt is nothing but the velocity of frame O dash with respect to frame O. Okay, so this I have got. Now because I am talking about the inertial frame, so while defining the inertial frame I will say that if I consider that this particular dr by dt, say my frame O dash, if I consider that my frame O dash is moving at constant velocity. Okay, so if my frame O dash is moving at constant velocity, so the meaning is that dr vector by dt is nothing but a constant term. Okay, so if this is a constant term, now if I take the second time derivative of this equation, it will be becoming d by dt of VO vector equal to d by dt of VO dash vector plus d square r vector by dt square. And ultimately, if my dr vector by dt is constant, it means the reference frame O dash is moving at constant velocity, then the second derivative of r will be equal to 0, because this is nothing but a non-accelerating frame. Okay, so in this situation I can say that the first derivative, which is this d by dt of v bar o, it will become the acceleration of the fluid particle with reference to frame O. Okay, and this will be equal to acceleration of the fluid particle with reference to frame O dash. So ultimately, when I will be writing the Newton's law of motion, which tells that sum of all forces is equal to mass times acceleration a naught. So this is for a frame at rest, and this is also equal to, because a naught is equal to AO dash, where AO dash is nothing but a moving frame at constant velocity. So this I will be able to write as AO dash bar. Okay, so ultimately I can say that if I have a frame of reference which is moving at the constant velocity, and if with respect to that frame we are trying to trace a fluid particle, for that also our acceleration of the fluid particle will remain identical to that of the acceleration of a fluid particle measured with reference to a stationary frame. So that is the reason that both these two types of frames, the ones which are at rest and the others which are moving with the constant velocity, are considered as the inertial frames of reference, and the Newton's law of motion is actually completely equally defined for both type of frames. Okay, now if I introduce the slight complexity over here, and if I say that this particular frame O dash is not moving at constant velocity, but say it is moving with variable velocity. Okay, so it is moving with variable velocity. So if it is moving with variable velocity, in that case I cannot say that dr vector by dt is equal to constant. So this statement is actually not true. So dr vector by dt is not equal to constant if this particular frame is actually moving at some variable velocity. Okay, so ultimately then this will give rise to the acceleration term, where when I am taking the derivative of velocity, so this particular equation will become over here as, this will become over here that acceleration of fluid particle with reference frame O is equal to acceleration of fluid particle with reference frame O dash, plus I will be having some additional component, and this additional component is coming because of the acceleration of the moving frame d square rt by dt square. Okay, so this type of frame, for this type of frame you can see now the acceleration of the fluid particle with reference to frame O and acceleration of with fluid particle with reference to frame O dash are different. So this is nothing but a non-inertial frame. So when I am talking about the non-inertial frame, I will be getting some additional acceleration term over here, and this additional acceleration term, say I am calling it as A vector R. So A vector R is the additional acceleration term which is coming into this particular system. So when this additional acceleration is coming into picture, so this is coming only because of the contribution, only due to the presence of the non-inertial frame. Okay, so any accelerating frame is nothing but a non-inertial frame, and this non-inertial frame will introduce certain amount of additional acceleration over here when I will be measuring with reference to a stationary frame. Okay, so ultimately what I can say is that when I will be writing now the Newton's law, then as per the Newton's law, sum of all forces is equal to mass into acceleration, but this acceleration is with reference to an inertial frame a naught. Okay, now this particular a naught, from the previous discussion I can replace it with a vector O dash plus d square rt by dt square, which I have given the name as a vector r. Okay, so ultimately I can write it as mass times of a vector O dash plus A vector r. Okay, so ultimately you can see that if I am talking about with reference to the non-inertial frame, particularly the Newton's law of motion with reference to the non-inertial frame, then this particular quantity A vector O dash will become nothing but sum of all forces, okay, minus this mass, and AR vector is coming over here, and this is equal to nothing but mass times acceleration vector with reference to a non-inertial frame. So this is, I can say that, nothing but Newton's law of motion for non-inertial frames. Okay. So when I am talking about the non-inertial frames, then I am getting one subtraction of a term mass times acceleration of the non-inertial frame AR vector, and this particular acceleration is nothing but coming because of the presence of the non-inertial frame of reference, and this type of force is called as fictitious force, or I can also call it as nothing but pseudo force. So this type of fictitious or pseudo force have to be subtracted from the net forces which are acting on a body, and then only we will be able to relate that net force equal to mass times acceleration of a fluid particle when measured with reference to a non-inertial frame of reference. Okay, so this is the important correction which one must introduce while we are talking about the non-inertial frames of reference. Okay, now another thing also comes into consideration, that the motion of a frame will not be always purely translational. Okay, so there can be, along with the translation, there can be rotation of the frame also. Okay, so when I am having rotation also, so ultimately my system will look something like this. If this is my xy z point O, now if I consider that I have both translation as well as the rotation, then this is my xyz system of some frame O dash. So now you can see this frame has linearly also translated. At the same point of time, this frame is having certain rotation also. So let me define that omega vector is the vector which is defining the rotation of this particular frame, and of course this rotation can be about any of the axis, x axis, y axis and z axis. Okay, so in this type of situation, whenever I will be defining the velocity of the fluid particle present in this particular frame, then I will be writing that velocity of fluid particle with reference to frame O is equal to velocity of fluid particle with reference to frame O dash plus dr by dt. This factor is particularly coming because of the linear translation of the frame, plus we will be having certain contribution because of the rotation of the frame, and the contribution which is coming because of the rotation of the frame, if you see, if you are having a rotating particle or a rotating mass, then ultimately that rotating mass contributes some tangential velocity to the system. So that tangential velocity will become nothing but omega vector cross r vector. So this is how I can define the total velocity of a fluid particle with reference to O is nothing but velocity of fluid particle with reference to frame O dash plus dr by dt, where dr by dt is coming because of the translation of the frame, plus omega times r dash vector, because now I am considering the rotation of the non-inertial frame. So that's why I will be considering this position vector also with reference to the non-inertial frame. So here I must write r dash. Okay, so this component is coming because of the rotation. Okay, so now if I have to find out the acceleration, then in order to determine the acceleration, I must do the time derivative of this equation. So I will be getting d by dt of vo vector equal to d by dt of vo dash vector plus d square r vector by dt square, and then I will be having this omega cross r dash vector, and if I do d by dt of this, then it will give me the many terms. So the first term will be d omega vector by dt cross r vector, second term will become plus 2 omega vector cross v vector, and third term will become omega vector cross omega vector cross r vector. Okay, so now let me give you the details of these individual terms. So the very first term of acceleration is coming because of the translation of the frame. So I can call it as nothing but the translational acceleration. Okay. Then I have second term. So what is d omega by dt? D omega by dt is nothing but alpha, angular acceleration. Okay. So angular acceleration multiplied by r is also another acceleration which we are getting. So this is coming because of the contribution of, this is the contribution of angular acceleration. Then this is another important quantity which is called as 2 omega var cross v vector is nothing but called as Coriolis acceleration. Okay, so Coriolis acceleration is another contribution which comes into picture, and this is identical to, if say particle is actually tied to a thread, and if we keep on rotating it, then we experience the centripetal acceleration which is equal to mr omega square. So centripetal force which is equal to mr omega square. So r omega square over here is nothing but referred to as the centripetal acceleration, and in vector notation it can be written as omega vector cross r vector. Okay, so this is my centripetal acceleration. So ultimately you can see that when I have a complex situation, it means the frame is undergoing through both the translation as well as the rotational motion, then whatever this a vector ar vector I will be finding. So this entire package is nothing but, this entire package is my AR vector. So AR vector will be having 4 components. One component will be because of the translational acceleration, other component will be because of the angular acceleration, third component will be of Coriolis, and fourth will be of centripetal acceleration. Okay, so these different types of acceleration will be coming into the picture for different type of flow situations. One simple example I can give you, if you talk about the surface of the earth, so any phenomenon if you are observing on the surface of earth, and if you consider some star which is far away from the earth's surface, and say it's a stationary star as nothing but your inertial frame of reference, then with reference to that particular frame, earth's surface is actually rotating. Okay, so as earth's surface is rotating, so of course it must have some component of the Coriolis acceleration, centripetal acceleration, or some angular acceleration. So if you talk about the magnitude of Coriolis acceleration for earth's surface is nearly of the order of 10 to power minus 5 times of g. So its magnitude is actually very, very small, extremely small. So because of this reason, majority of the small scale phenomenon which we study on the surface of the earth, this particular Coriolis acceleration term is actually neglected. Okay. On contrary, if we talk about the large scale flows such as the flow of fluids which are taking place at the geographical scales and at the ocean level, then under these scenarios for oceanographic and geographical flows, actually we have to consider these effects into account. Okay, now ultimately, so out of this equation I have simply got that my a vector O will be equal to a vector O dash. This is acceleration with reference to non-inertial frame. Please make one correction that this r vector is nothing but over here r dash vector. Okay, so this will be equal to the AO dash vector plus AR vector, and this AR vector is having 4 different components, and depending upon the presence of a single component, actually we have to consider the individual one. Okay, so now utilizing this information, if I have to write down now the law of, or say I can say, if I have to write down the Reynolds transport theorem for a control volume in non-inertial frame. Okay, non-inertial frame, particularly using linear momentum as the property. So linear momentum I am using as property. So ultimately what I will be getting is that my sum of all forces acting on a control volume minus AR times dm and its integration over the control volume. So that will be my left hand side, and this must be equal to rate of change of momentum within the control volume. So that is d by dt of cv v vector rho dv bar plus across the control surface if I have any flux of the momentum, linear momentum. So flux of the linear momentum can be written as v vector rho times Vr vector dot n cap into dA, and this Vr vector I am referring to nothing but V vector as function of position and time minus V surface vector as function of position and time. This I have already described to you, and if I consider that my control volume is fixed, if control volume is fixed, it is not moving, then Vr vector will become simply equal to V vector, and ultimately my last term of the flux Cs V vector rho V vector dot n cap into dA I will be getting simply. So this last term will be simplified to this one only. If my control volume is fixed, it means it is not moving, fixed as well as the non-deformable. Okay, so if these two conditions are satisfied, then this will be my linear momentum equation. Okay, so now as we have already discussed about the non-inertial frame, so let us also try to see that what is the utility of this non-inertial frame of reference. Okay, so one major utility of the non-inertial frame of reference you will be finding in the rocket propulsion. So when we have a rocket, we see that rocket takes off from the surface of the earth. Okay, so when rocket is taking off from the earth's surface, if I consider all the different velocities of the gases which are coming out of the rocket with reference to earth's surface, our analysis will become complex. So one of the easiest way to analyze is we can fix our reference frame on the surface of the rocket itself, and we can analyze different flow parameters with reference to that particular moving frame, which is actually moving with the velocity equivalent to that of a rocket. Okay, so and also because the rocket, while it is taking off, it does not moves at the constant velocity, it moves at the variable velocity, and it will be having certain acceleration. That's why whatever the frame of reference which we are fixing on the surface of the rocket, that will be nothing but a non-inertial frame of reference. Okay, so to analyze this situation, what I can do, I can consider rocket. So this is my rocket, and say this rocket is having some initial mass m naught, and initially its velocity was 0 at time t equal to 0, and say in the question it is asked that you have to determine velocity v of t. So basically our task is to calculate the velocity v of t of a rocket. Okay, so how I can do is that I can consider that, and also say it is given in the question that exhaust gases are coming out at mass flow rate of m dot. So m dot is mass flow rate of exhaust gases which are coming out of the rocket, and v is velocity of exhaust gases, and this velocity is with respect to rocket. So when I am measuring with reference to the rocket, then velocity is v. So I can consider that some of the exhaust gases are going out with mass flow rate m dot and velocity ve. Okay, so this is something which is happening over here. Okay, so now if I take a control volume around this rocket, so what will be happening? If my rocket is moving at velocity vt, then of course the control volume will also move at velocity vt. Okay, and also because I am measuring the velocity of the exhaust gases with reference to the surface of the rocket, that's why my frame of reference, which now I am considering, is nothing but a moving non-inertial reference frame. Okay, so now one system I can connect over here. Say this is my z coordinate, and gravity is acting in downward direction. Okay, and also let me write the initial mass of the rocket is m naught, but if I have to calculate mass of the rocket at any time m of t, say I am writing it simply as m, that will be nothing but initial mass was m naught, and mass was going out of the rocket at velocity m naught, at mass flow rate m naught. So minus m naught times t is the amount of mass which has gone out of the rocket during time t. Okay, so now mass is also continuously going out of this rocket. Also consider that in this situation, the flow within the rocket is nothing but steady. So we have steady flow and incompressible flow situation. So these are the another two assumptions which I have invoked over here. Okay. So now what will be happening? If I have to analyze this particular situation, the first important point we have to remember is the velocity Ve which I am considering over here. This is nothing but with reference to the rocket surface, and rocket surface is my non-inertial frame of reference because it is moving at some variable velocity V of t. Okay, so it means that whenever I have to apply over here the force balance or the RTT for a control volume to write down the Newton's second law of motion, I have to write this for a non-inertial frame of reference. Okay, so what I can do is that if I write over here sum of forces minus integral a vector r, AR I have to consider over here, times a vector r times dm integral over the control volume, that will be equal to d by dt of integral over control volume rho v vector dv bar plus integral over the control surface v vector rho v vector dot n cap into dA. Okay, so now ultimately, so this is the equation. Now ultimately what I will be getting, so if you see this particular equation I am applying in nothing but I have to now apply this particular equation in z direction. Okay, why in z direction? Because you can see the rocket is actually moving in z direction. So if I apply this equation in z direction, my sum of the force, so you can see another important assumption we will be considering over here, that air drag is negligible. So my air drag is also negligible. So once I consider that air drag is also negligible, then what ultimately I will be getting is that the net force acting at this rocket at any moment at any time t will be nothing but downward weight of the rocket. So weight of the rocket is m into g minus m into this residual acceleration AR. Okay, and rocket is moving in upward direction, so of course this acceleration will be in upward direction, but I have to use with minus sign, so minus of m into AR over here. Okay, and this will be equal to, for steady flow conditions, because I have already taken the assumption of steady flow, so this will be equal to 0. Now I have to take this second integral across the control surface, and if I consider this integral, then you will be finding that in this entire surface of the rocket only we have one term through which actually mass is going out of the control volume or control surface. So that is nothing but m dot is mass flow rate and v is the velocity. So this is nothing but the assumption of a 1D flow. So it is given that at each and every portion of the outlet gases are coming at an average velocity of Ve. So if this is the assumption of a 1D, then I can simply write this term as nothing but mass flow rate at the exhaust, that is m dot times velocity. And if you see, the z axis is positive in upward direction and velocity of the exhaust gases is in downward direction. So as velocity of exhaust gases is in downward direction, I have to write over here minus Ve. Okay, so from here I will be getting that this AR I can write as nothing but, let me take this mg to the other side, or I can write m times this AR I can write, because AR is nothing but the acceleration of the non-inertial frame, and non-inertial frame is fixed on the rocket, so it will be d by dt of v of t, which is velocity of the rocket, and this will become equal to, if I take this negative sign, then it will become m dot into Ve. Okay, so m dot times Ve, this will become positive, and this mg is also going the other side. So it will be remaining the same. Sorry, it will take the negative. Okay, it will also remain the same. Yes, plus sign. So plus m into g. So now what I can do, I can write dvt by dt equal to m dot by m times ve plus m by m will cancel g. Okay, so ultimately what I will get, I will be getting that integral of dv, and this integration, because corresponding to time t equal to 0 my velocity was v equal to 0, and at any time t my velocity is v of t, so limits of integration will be from 0 to v of t, and this is equal to integral ve into m dot divided by this m. M is mass of the rocket at any time t. So this already I have specified that m will be equal to nothing but m naught minus m dot into t. Okay, so this I can write m naught minus m dot into t, and dt, this is integration from 0 to t, plus integral g dt from 0 to t. Okay, so this is the important equation which I will be getting over here. Just a correction, so I think this term will be nothing but minus m. Okay, so here I will be having a negative sign. Why? Because this force is also acting in downward direction, so this g must have a negative sign. Please make this correction, because gravity is acting in downward direction, so this z is positive in upward direction, so the force mg should come over here with a negative sign. So as it will come with negative sign, I will be having over here minus mg. So this will be then minus g, and this sign will also be minus sign. Okay, so now if I do this integration and substitute the limits of integration, ultimately I will be getting my velocity t as nothing but minus ve times ln of 1 minus m dot t by m naught. Okay, so that is my velocity and minus g of t. So this is one classical equation in rocket mechanics. Okay, so when we study the rocket dynamics problem, this equation is very important in determining the velocity of the rocket, and you can see why I have discussed this case over here, because this equation is nothing but, this problem is helping us in identifying the applications of Reynolds transport theorem whenever it is applied on nothing but a non-inertial frame of reference. Okay, so now apart from the linear momentum, another important property of the fluid is there, which we call as angular momentum. Okay, and if you see the definition of the angular momentum, I can call it as h vector. It is nothing but r cross times v vector into dm and integral over the control volume. Okay, so ultimately when we talk about the angular momentum in case of the solid particles, so this angular momentum finally reduces in the form of mass moment of inertia. Okay, but this mass moment of inertia does not help us for fluid mechanics problems, because mass of fluid particles is not constant, it is always changing for a control volume depending upon the local flow field. Okay, and also the particles whatever we are considering, the fluid particles which we are considering, these are not rigid. Okay, so fluid particles are nothing but deformable. So that's why whenever for a fluid medium I am defining this angular momentum, I am considering r cross vector v vector times dm, and then I am integrating it over the entire control volume. Okay, so whenever we will be considering this cross product of r vector dot v vector, so of course this position vector must be measured with reference to certain point. Okay, so let me consider that I am measuring this reference this position vector with respect to some point O. Okay, so if I am measuring this with respect to point O, so of course my angular momentum, whatever I am calculating, that will be also with reference to point O. Okay, and the way we define Newton's law of motion for inertial frames of reference in case of linear momentum, in a similar way for angular momentum I will be getting that dh naught by dt is equal to sum of all the movements, because I am considering h naught, it means angular momentum about point O. So that's why whatever the movements I will be considering, these movements also should be considered about point O. So the meaning is, if about point O any forces which are acting on the fluid particle, so whatever movements these are causing, so the net sum of all these movements must be equal to rate of change of angular momentum for that particular system. Okay, so now this is nothing but this dh by dt is applicable for a system. So now it is given in the form of system, but ultimately when I will be analyzing the fluid flow problem, I have to apply in the form of control volume. So for analyzing the fluid flow problem, what I have to do, I have to convert this dh bar naught by dt from system approach to control volume approach, and for doing this I will be using the RTT. Okay, so when I will be applying the RTT, so ultimately what I have to do, I have to consider the property. So property is h naught, main property, which is my angular momentum, and ultimately it can be written as nothing but r vector cross v vector times dm over the entire control volume. Okay, and when I will be considering the property per unit mass, so if I consider h naught per unit mass, then it will be becoming as nothing but r vector cross v vector only. Okay, so now with this information, what I can do, I can apply the Reynolds transport theorem over here. So I will be writing that sum of the all moments about point O will be equal to d by dt of property per unit mass basis, that is r vector cross v vector times density into dv bar plus integration over the control surface r cross v vector times density into vr vector dot n cap into dk. So this is nothing but my famous equation of angular momentum, which will give me the net amount of movements which are acting about a point. Okay, so whenever I will be talking about the movements, I can write the sum of all movements as nothing but sum of r cross f vector, r vector cross f vector about point O. Okay, so because movements will be acting only because of the force, and force into perpendicular distance is nothing but my movement. So r vector cross f vector about point O will be forming my movement, and this will be equal to d by dt of integral over the control volume r vector cross v vector times rho into dv bar plus control surface r vector cross v vector rho v vector dot n cap into dA. So now what assumption I have taken? I have taken that control volume is fixed and non-deformable. So if I consider these two assumptions, then VR I can replace simply with nothing but V. Okay, so this is the famous equation. Now the application of this famous equation comes in nothing but my different systems, and major applications comes in turbo machines, or which we call as fluid machineries. Okay, for example, you see this electricity is coming from hydropower plants, and in hydropower plants we are having the turbine blade. Over that turbine blade, fluid is actually applying certain amount of power, and then it is producing a torque. So if you have to determine that how much torque is generated by the flow of the fluid over a turbine, then you can apply this particular equation of angular momentum. Similarly, at our home we use the centrifugal pump for majority of the water pumping applications. Okay, so if you have to determine that, if say you know the velocity at which water is approaching the impeller of a pump, and if you know the velocity at which water is going out of the impeller of the pump, and you have to determine that how much torque has to be applied on the pump in order to keep it rotating, okay, so that water is entering and leaving at the desired conditions, then what you have to do, you have to do certain mathematical analysis, and of course mathematics is nothing but language of for physics. So this physical phenomena can be mathematically represented in the form of this uh, angular momentum equation, and you can apply this equation for solving that particular problem. Okay, so how to do that, that I will discuss in the next class. Okay, and now we will stop at this point.